Proofs by induction are seen quite frequently in discrete math and linear algebra. Proofs by induction are based on the principle of induction, and the principle of induction can be based on the well-ordering principle. Let's see how we can prove many things at once. There's two ways to prove many things at once. First, one can prove one claim about many numbers. For example, to prove that for all real numbers x, y, and z, x plus z equals y plus z implies that x equals y, we must prove one result for many real numbers. The way to do this is to prove the claim for an arbitrary or typical choice for each variable. Second, we could prove a sequence of related claims. The way to do this is to construct a proof by induction. A proof by induction is based on the principle of induction. The principle of induction is more useful but less intuitive than the more or less equivalent well-ordering principle. The well-ordering principle is the foundation of this talk. Okay, here it is. The well-ordering principle. Any set of positive integers contains an integer smaller than all the others in the set. So if I choose 5, 6, 7, 5 is the smallest one. I can't set up any set, even it will say all the integers greater than 6. 6 is going to be the smallest one. You choose any set. There's always going to be a smallest number in that set. This principle, in fact, is what distinguishes the integers from the rational numbers. For example, there are rational numbers between 0 and 1, and they can get closer and closer to 0. There's no smallest rational number, but there's no integers between 0 and 1. Why are there no such small integers? There are no such small integers because of the well-ordering principle. Here's a proof that there are no integers between 0 and 1. This proof is similar to the proof used to prove the principle of induction, but it's a little bit simpler. Suppose that there's a small integer x. We're doing this to get a proof by contradiction, in which we're going to argue to a contradiction and claim that this supposition is false, thus proving the theorem that there's no such small integers. So suppose there's a small integer x such that x is greater than 0 and less than 1. Well, consider the set of all such integers. This set is not empty because x is in it. By the well-ordering principle, this set has to have a smallest integer. Call that x sub s. Because x sub s is less than 1, and because it's greater than 0, so it's positive, we can multiply both sides of the first inequality, x sub s less than 1, by x sub s itself. So we get x sub s times x sub s is less than x sub s times 1. That's x sub s squared is less than x sub s. This means that x sub s squared is a small positive integer, even smaller than supposedly the smallest one, x sub s. This contradicts the requirement that x sub s is the smallest. Therefore, we found a contradiction. Our supposition must be false. There are no such small integers. This proof, as well as the ones that follow, relies on a certain pattern of logical reasoning that I refer to as the affirmed premise deductive pattern. Let's look at that just to review what it says. But it works for any propositions P and Q. It's sort of a pattern in logic. If we know that P is true and that P implies Q is true, those are the two premises, then we're guaranteed to have the conclusion Q also being true. The claim is that the truth of these two premises guarantees the truth of the conclusion. For us, what this means is if we know that P implies Q is true, and we can affirm that the premise P is true, then we also know that the conclusion Q is true. Okay, let's apply all this to the principle of induction. Let's first figure out what it is. This theorem or principle says, well, if we start off, we're given a sequence of propositions, P1, P2, P3, Pn minus 1, Pn, one for every positive integer. Now, the claim is going to be, we're going to have two premises and a conclusion. The two premises are that P1 is true, and the second premise is that for every integer n greater than 1, P of n minus 1 implies P of n. It's a domino principle. It says it says P of 2 implies P of 3, P of 3 implies P of 4, P of 4 implies P of 5, and on down for every n. Now, if these two premises are true, then it's guaranteed that P of n is true for every single integer n greater than or equal to 1. We can prove, this can be proved using the well-ordering principle. It's a little complicated. It's an implication with two premises and a conclusion. And this is one reason that the principle of induction is a little less intuitive than the well-ordering principle. Okay, let's look at the proof. It's a proof by contradiction, so we suppose the principle of induction is false. How can it be false? The claim is an implication, and the only way for an implication to be false is if the premises are true somehow, or premises are true, and the conclusion is false. That's the only situation in which the implication is false. So the two premises are P of 1 is true, and for every integer n greater than 1, P of n minus 1 implies P of n. So if we've supposed it's false, we're going to suppose these two premises are true, and we're going to suppose the conclusion is false. The conclusion is that P of n is true for every integer n greater than 1. How can that be false? Well, P of 1 is true from the first premise, so that can't be false. But there must be at least one integer j greater than 1 for which P of j is false in order for the conclusion of the theorem to be false. If it's false that if P of n is true for every integer n, all we have to do is find one P of j that makes it false to make the conclusion false. Okay, so under the supposition that the principle of induction is false, we have to assume that there is one of these propositions is false, namely P of j. Consider the entire set of these integers greater than 1, which label false propositions. The set is not empty. Well, j is in it. Therefore, the set has a smallest element by the well-ordering principle. Let's call it j sub s. Now we're set up to get a contradiction. Because j sub s is greater than 1, the integer js minus 1 greater than 1 is greater than or equal to 1, also labels a proposition, even if js is as small as possible, that is 2 minus 1 is 1, and P of 1 is a proposition. So P of js minus 1 is a proposition. Pj sub s is the false claim with the smallest index. So Pj of s minus 1 has a smaller index, so it must be true, no matter what j we've chosen. Okay, the second premise, which we are supposing to be true, can be evaluated with n equals j sub s, and it reads P of js minus 1 implies P of js. Now, we know that Pj of s minus 1 is true, and we know that P of js minus 1 implies P of js. So by the affirmed premise pattern, we know that P sub js is also true. But this is a contradiction. P of js cannot be both true and false. This means that our supposition that there's at least one integer greater than 1 for which Pj is false must itself be false. Therefore, P of n is true for all n. Now that we've established the principle of induction, how is it used? Well, here's a simple sequence. Here's a simple example. Here's a sequence of simple claims. The first proposition is 5 equals 1 times 5. The second proposition is 5 plus 5 equals 2 times 5. The third proposition is 5 plus 5 plus 5 equals 3 times 5, and so on, down to P of n. We have n 5s, and that equals n times 5. How can we prove these intuitively obvious results, that they're all true? Let's attempt a proof by induction. What we need to prove is the conclusion of the principle of induction, that all the statements in the sequence are true. If we can prove, since we know the principle of induction is true, it's an implication, and the conclusion of the principle of induction is what we want to prove. What we actually need to prove is just the first two premises of the principle of induction for this sequence. We need to prove that they're true. Then the principle of induction and this result proves the result we seek from the affirmed premise pattern. Okay, so we're going to try to prove the first two premises. 5 equals 5 is a basic arithmetic fact. Therefore, the first premise, P of 1, is true. Now we must prove premise 2, that for each integer n greater than 1, P of n minus 1 implies P of n. This is one formula to be proved for all values of n. We can do this by showing it is true for an arbitrary integer. Let's prove it for the arbitrary value j greater than 1. So we must prove that p of j minus 1 implies p of j, where j greater than 1 is the typical value. Now, this is an implication, and to prove an implication, we assume the condition, p of j minus 1, and prove the consequence, p of j. Okay, on the last slide, we were about to prove this implication, and we're going to prove it by assuming the premise, p of j minus 1, and showing that the conclusion has to be true for arbitrary j greater than 1. So suppose the condition is true. Well, the condition, p of j minus 1, is that we have j minus 1 fives, and they equal j minus 1 times 5. Now, we're going to consider the expression p with 5 j's, which is the left-hand side of pj, okay? And so that's starting on the left-hand side, and we can peel off 1 5 and see that that's equal to p to 5, to j minus 1 fives plus 5, and the expression there, j minus 1 fives, is the same as the left-hand side of p of j minus 1, so we can replace that sum with j minus 1 times 5. So we have j minus 1 times 5 plus 5 is equal to the far left-hand side, and we can then factor out the 5 from those two expressions to get j minus 1 plus 1. The ones cancel, and we have j times 5. Well, the left-hand side is the left-hand side of pj, and the right-hand side is the right-hand side of pj. So this proves the claim that pj is true. This means we've proved the consequence pj for arbitrary j, so the implication is true. In turn, this means that we've proved p of n minus 1 implies pn for all n. We've shown that both premises of the principle of induction are true for this sequence. And because both premises of the true for this sequence are true, from the affirmed premise pair, we can conclude that the principle of induction itself implies that the conclusion of the principle of induction is true, that the sequence of claims above is true for all n. Okay, this is the most complicated proof pattern we have seen so far, and is used far and wide in linear algebra, discrete math, and many areas of other areas of mathematics and computer science. A close relative in computer science appears in the construction of recursive functions. Though complicated, it is powerful.